yesterday that definite integrals tell us the area under the curve. So for number 1, this basically asks us what's the area under the graph of y equals 4 from -3 to 6. So if we draw this graph from -3 to 6, and we have the line y equals 4, we want to know the area under that line from -3 to 6. So this one's pretty simple. We just have a rectangle. Right, and this rectangle, the base of this rectangle would be 6 minus -3, which is 9, and the height is 4. So the area is 36. That means this definite integral is equal to 36. Similar is number 2 here. We have the definite integral from 4 to 9 of dx. So that's like having 1 times dx. So in this case, we just have the line y equals 1, and we want to find the area under that line from 4 to 9. So again, just dealing with the basic rectangle. Base is 5, height is 1, so our area is 5. So our definite integral is equal to 5. For number 3, now we just have a constant c. So we're doing this a little bit more in a general form. For this one, going from A to B, and the line y equals c. Well, again, we end up with a rectangle here that we're trying to find the area of. The base this time, just like we did with number 1 and number 2, we took b minus a, right? The rightmost point minus the leftmost point. That's our base. This time we can't get a simple number. We just have to leave it as b minus a. And the height is that constant, just like the height here was 1, height here was 4. So for this, area of our rectangle, the area under the curve, is b minus a times c. So down here, theorem 4.21, we pretty much showed that one with number 3. It's the same thing. If c is a real number, that constant there, and we're taking the definite integral from a to b of c, then that's just going to be equal to c times b minus a. Alright, so that works for any type of a constant, any definite integral like that. Now, for the next 3, a little bit different, but it's going to help us with theorem 4.22. If you look at number 4, this time, our function is y equals x. I'm trying to find the area under the graph of y equals x from 0 to 6. So y equals x, just a line with a slope of 1. So we're looking for the area under that line. From 0 to 6, we end up with a triangle here. Again, easy to figure out by hand. Base of the triangle, 6. Height of the triangle is going to be 6. So our area is 6 times 6 divided by 2. So we get an area of 18. Now, number 5 and 6 are similar. They're just lines, but they have some different slopes. They're also going from 0 to 6. I want you to go ahead and find the areas, evaluate these definite integrals for 5 and 6, and see what you get. Alright, let's go ahead and take a look. Number 5 for this one. Our equation or line is 2x. So slope is 2. This time we're going to go all the way up to 12 here. If we put 6 in, 12, 0, we have 0. So our line's a little bit steeper. And to find the area of this triangle, base is 6, height is 12. So 6 times 12 divided by 2, we get 36. For number 6, we have 1/3 x for our line. So this one starts at 0, 0, slope of 1/3, up 1/3, up 1/3. So we want to find the area under the graph right here, this little triangle. Base of 6 again, height is 2. So the area, our definite integral, 6 times 2 divided by 2, we get an area of 6. Now, with this one, let's look. Each of these is x, but we have 2 times x and a 1/3 times x. You notice anything about these problems? Here we had 18 for our definite integral. This one we multiplied by 2, so it's 2x instead of just x, and our area doubled. For this one, 1/3 times x, we have 1/3 of 18. So just like a lot of the other things we've talked about, when we have a constant inside this definite integral, we can pull it out. We can put it out in front of that definite integral. Alright, I'd like you to go ahead and try 7, 8, and 9. Evaluate each of these integrals by finding the area under the curve, just like the ones we've been doing. Alright, let's take a look. Each one of these is a definite integral from 0 to 4. First one is just x. So from 0 to 4, we just end up with a triangle. Right? We have our line y equals x, going from 0 to 4. So just looking at this area, so we have 4 times 4 divided by 2. So we get an area of 8. For number 8, this one we have a constant term in there. We could just use our formula up above or look at the graph here. From 0 to 4, we end up with a rectangle. Base is 4, height is 3, so we get an area of 12. So definite integral from 0 to 4 of x is 8. Definite integral from 0 to 4 of 3 is 12. Well, here we have x plus 3. So you might think that that should come out to be 8 plus 12. Let's check and make sure. For this one, x plus 3, we have a line starts at 3 with the slope of 1. So we have a line right here. And from 0 to 4, we end up with a trapezoid here. But that trapezoid can be broken into two parts, a rectangle and a triangle. Well, this rectangle down here is 4 by 3, just like this one. And this triangle has a base of 4 and a height of 4, just like this one. So this area does end up being the same. We get an area of 20. Another way we could do it, area for a trapezoid, base 1 plus base 2, so 3 plus 7, times the height, which is the distance between the two bases, which would be 4, divided by 2. So we still get 20 that way. So that goes to show theorem 4.23. Just like with indefinite integrals that we talked about before, same property is true, that if we have definite integral with addition or subtraction, we can break it up into two separate integrals. Whether it's addition or subtraction. Alright, let's take a look at the back. For this one, these problems, it asks us to use the facts to the right to evaluate each of the following integrals. So actually, these facts below. It tells us that from -1 to 5, the definite integral from -1 to 5 of x squared dx is 42, and the definite integral from -1 to 5 of x dx is 12. So what we can do here for these 10, 11, 12, and 13 is kind of break these down using those theorems that we've talked about. We can rewrite this as the definite integral from -1 to 5 of 4x, or we can bring that 4 out in front, minus definite integral from -1 to 5 of 7 dx. So that constant out in front just stays 4. We know from up above here that the definite integral from -1 to 5 of x dx is 12. And for this one, when we have a constant, it's just going to be that constant times b minus a, so 5 minus -1. Same as plus +1. So we get 48 minus 7 times 6. So we get 6 for this one. For number 11, again, we can break this up. We can look at the definite integral from -1 to 5 of 2x squared. We can put the 2 out in front, times x squared dx, minus 5 times the definite integral from -1 to 5 of x dx. So we have 2 times definite integral from -1 to 5 of x squared is 42, minus 5 times the definite integral of x is 12. So we get 84 minus 60, which gives us 24. Alright, go ahead and try 12 and 13 on your own. Alright, let's go ahead and take a look at these. Number 12, this one can be broken up into 3 separate integrals. So we're going from -1 to 5 for x squared dx minus 3 times the definite integral from -1 to 5 of x dx plus the definite integral from -1 to 5 of 5 dx. So x squared, remember, is 42 minus 3 times the definite integral from -1 to 5 of x is 12 plus constant, we're taking the constant times 5 minus -1, same as plus +1. So we get 42 minus 36 plus 30. So we end up with 36, yep. Alright, number 13. This one we have to multiply this out first. So 2x minus 3, that quantity squared, gives us 4x squared minus 12x plus 9 dx. Now it's just like number 12. We can split it up. We have 4x squared, so we can bring the 4 out in front, times x squared, minus 12 times the definite integral from -1 to 5 of x, plus the definite integral from -1 to 5 of 9. And I forgot the dx's here. So 4 times, we have 42 for that definite integral, minus 12 times 12, plus 9 times 5 minus -1. So 4 times 42 gives us 168 minus 144 plus 54. So that gives us 78. So that gives us the area under that curve. Alright, let's take a look at these next 3 here. I want you to go ahead and try each of these, evaluate each of these integrals. You'll notice it's the same thing on the inside of the definite integral. The difference is the lower and upper limits. Goes from 0 to 3, then 3 to 7, and then 0 to 7. See if you can figure anything out about these after you're done with all 3. Alright, check. Number 14 should get 4.5. Just get a little triangle there. 3 times 3 divided by 2 gives 4.5 for the area under the curve. 15 is 20. We have a trapezoid, so base 1 plus base 2 times the height, distance between the bases, is 4 divided by 2. That gives us 20. And then 16, big triangle, base times height divided by 2, we get 24.5. So we can see that if we go from 0 to 3, and then from 3 to 7, if we combine those two, we get the same area over here. And you can kind of see it with this little triangle. We fill this in, that gives us the whole big triangle when we put those two together. And that kind of proves this next part here, theorem 4.25, that if f is integrable on a closed interval and a, b, and c are any three numbers in the interval, then the definite integral from a to b of f of x dx is equal to the definite integral from a to c of f of x dx plus c to b. So as long as these two are the same, then this definite integral is equal to the sum of these two definite integrals. So, almost done here. A few more problems to look at. For this one, number 17, we're supposed to express this as one integral. So if we're doing this from 3 to 6 and then 6 to 11, we can write this as definite integral from 3 to 11 of f of x dx. For 18, negative 2 to 5, and then from 5 to 3, even though these kind of go backwards from a larger number to a smaller number, as long as these are the same, we can use this theorem. So from negative 2 to 3 of f of x dx. Alright, we're going to skip 19 for a second. Let's go down to number 20. For this one, notice, remember that these two numbers right here, the upper limit of the first one and the lower limit of the second one, have to match up. So the c and c. In this example, it doesn't work that way. Plus there's a minus. So that 5 and negative 4 doesn't work. Now what we need to do for this one is we have to go ahead and change this from subtraction to addition. Remember that the minus here, we can change this to a plus if we switch these two around, the upper and lower limit. So we would have the definite integral from negative 4 to 5 of f of x dx plus definite integral from 3 to negative 4 of f of x dx. Problem is, still doesn't match up correctly. Right? Remember, this upper limit is supposed to match this one, but that's not how it is. But we can accomplish that by switching these two around. So we write it as the definite integral from 3 to negative 4 of f of x dx plus the definite integral from negative 4 to 5 of f of x dx. Now these match up. So we get the definite integral from 3 to 5 of f of x dx. Same kind of thing here with number 21. You have to do the same thing with 22. This one, it's already a plus. We can't change it to the switching those limits, upper and lower limit. But we can go ahead and just rearrange the order in which we're adding these. So definite integral from f to d of f of x dx plus the definite integral from d to e of f of x dx. So this one comes out to the definite integral from f to e of f of x dx. Alright, go ahead and try 19 and 20 on your own, please. And then we'll check them, and we will be done with notes. Alright, check number 19, you should have definite integral from negative 3 to 7 of f of x dx. And for 21, definite integral from 2 to 5 of f of x dx. Alright, homework for this weekend, page 395, number 3 through 10 and 17 through 21. Also, you have the AP worksheet that will be due next Friday. Have a good weekend.